Remember, if you don't want to be recorded, turn off your camera. If you want to be recorded, feel free to leave your camera on. Uh, uh, but let's get started. Okay. So welcome to week 5. We're going to talk more about filters. We're going to talk about folds and some new notation and some new or some things you might have seen, but we're going to go in detail about why they might be useful now, like the where and let and things like that. And we'll get into the details here. So what coffee are we drinking? Is anyone drinking coffee today? I think Matthias isn't here. So I know he's probably drinking coffee on the road, but I'm not sure. Alex, you've got is it water or beer? I can't tell.
This is water.
Water. All right. So yeah, no, you don't have to drink coffee. I already drank my coffee, my iced coffee. It's hot here in Southern California, so we definitely need our iced drinks. Let's see. I know if Nori were here, he'd probably be drinking his chaga infused coffee. But anyway, so let's move on. We're going to look back at last week. So last week we started tackling, and a number of you put your homeworks up on the Discord. Oh, let me make sure I can open my chat here. We discussed last week sort of filtering out some things like spaces or punctuation, or who knows what. The apostrophe. Anyway, so those were things that we discussed last week that didn't really fit into how we were checking if something was a palindrome, right? We capitalized everything and then we didn't do anything else, and then we removed spaces, and that was great, but we had all these other problems, and so we'll take a look at maybe a sample of what this all together might have looked like. This is not the way that I would encourage you to do it. We had that is palindrome from before. We had the humane maybe that said whether or not something was a palindrome. We had this idea of maybe removing things that weren't our A to Z. So say you had say you had A to Z alphabet and you wanted to keep those and get rid of other things. How did you do that? Maybe you had some case statements. Maybe you had some nested case statements. Just don't do the nested case statements if you can. Nested case statements are messy and really problematic, and you've got to make sure your spacing is correct, and it's just too many problems. Anyway, well, we had that all uppercase where we used the map function, and then if we wanted to put all those together, we would have we would print out the maybe condition of the is palindrome, of the all uppercased version of the removed character of the characters that were left after we removed some other characters of that original input from the get line, and that was great. But how we did that, remove not A to Z, if we don't have this nested case, well, let's take a look at different options for that. So we have this idea of a filtering function. Yes, we covered what filter does, but here is what we said. Okay, filter says if some condition is true about the filter, then we or not true, depending on how you're filtering out or you're filtering in. And then if something is true, if we're filtering in, then we keep it, and then we just filter the rest of the tail of the list. And if it isn't true, then we ignore the head and we go on to the tail. But we learned there were some built-ins already, right? We learned that there was filter by something of some list, right? And we could do filtering of out of spaces. So if we had filter and then we had some condition, and the condition could be some function that says when X is not equal to a space, we keep it. And so if we had this input of a string with A comma space B prime space X, this would return the A comma B prime X without spaces, right? And that works. And then we said, well, then we've got to filter out the commas. And so if we had A comma space B prime space X, if we're filtering out those commas, we would return A space B prime space X. Notice that I didn't put the \X and then the X not equals comma here. And this is what's called an eta conversion or eta conversion, depending how you pronounce it. And eta conversion says if you can remove the variable name and still understand what the function is, then you can convert the function to a simpler version of the function without the argument. So not equals comma is the same as, well, an X is not equal to the comma, because we'd assume that there would be something that was not equal to the comma. And if we know that there's something that's not equal to the comma, that's probably the argument to the function. And so if we know that there would be an argument to the function and that function would be checked not equal to comma, we can just ignore it. We can just leave out the X altogether. And that's something that's unique, you might say, to Haskell or to functional programming languages that have this eta conversion method, where you make these lambda functions, these nameless functions, right? That that really are super simple, and it's really compact. And so then we could do this for each element that we don't want, right? We could filter out, you might end up with something like this. Okay, remove commas, filter not equal comma, and then remove spaces, filter not equal space, and then remove exclamation, filter not equal exclamation. And then you might get remove semicolon, filter not equal semicolon, and then dot, 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 dot. Some people sort of chose a similar method when they were removing characters from the string that you're checking if it's a palindrome. And this is totally fine, right? The idea is totally fine. But the problem is there's a lot of functions that you'd have to write, right? So you don't know how many functions you have to write. And so you'd end up with a lot of functions, and then you'd have to call each of those functions one after another, however many removes you created around the X, and then check the is palindrome of those values. And that's fine, right? But we try to, in Haskell, just like with those eta conversions to make a shorter function, we like to make things as simple as possible. And so this may not be the most simple thing. And so there may be alternatives. Well, maybe we can make it more generic. Maybe we can create this thing called remove character. And it would take a character that you're removing, and it would take some list of the characters, and then it would produce another list of the characters. So, right, instead of char there, we might have string, right? And so if you notice here, I did another eta conversion. And the eta conversion here is we have this rem char, and you might say from the signature, well, it takes a character like that X, and it takes a list of chars, but I don't have a variable in there for the list of chars. And that filter doesn't have a list of chars like I did here. I didn't include those lists of chars after the filter. And you can do that with Haskell. So then you would apply that rem char onto some character onto a string or onto a list of chars or whatever you're removing from a list of whatever. But you're still stuck with is palindrome, remove char, and then you have to list the character out. It's still too much, and still too confusing to the reader, right? It's still a lot of separated things. And so some people in their homework, right, they said, well, that's great. What if I could make a list of all of these characters I want to remove, and then just remove them all at once? And then you could recurse through the list of characters that you wanted to remove, and then you'd be able to come up with the solution of what are those characters I want to remove, or how do I remove those characters that I want to remove? And so you might have this remove characters function that takes a character list and takes an input string and produces an input string at the end. And what you do with this these characters that you're trying to remove, well, you have some case statement that's going to do a recursion, and when there's no more characters to remove, well, then that's just the empty list, right? And so that would get tacked on to the end of whatever we have. And then if there were some characters, right, if there were character and rest, right, if there was this character to remove, then we would do that rem chars of the rest, and we would apply it to the removed character that we defined here, of the character that we're removing from the input. So if we notice here, rem char of the character we're removing from the input, what does that produce? It produces a potentially shorter list of input, right? So if that character exists inside of that input, it's going to remove it from the input, and then it's going to return that value. And since we have that $sign there, everything on the right of the $sign gets computed first, and then that input is then passed into rem chars of the rest. And that new input is a shorter list of input, and then it calls that function rem chars again with the rest of the input. And so therefore, we get a shorter list of not just rest, but a shorter list of input. So we're actually potentially getting a really, really much shorter list. And the way we would call this function is we would say is palindrome remove chars, rem chars, and then we would have a list of bad characters, right? Whatever they are. And that could be a long list, right? And who knows what they are? And then we would apply that to the input. And the input is whatever we got from the get line. And that's great, except the list of characters is still pretty long, and may be confusing, and we may miss some, and we may not know what all the characters are. And so sometimes when your inputs are too long to exclude, you have to think and say, what should I include instead? So one way to include instead of exclude is to say, oh yeah, regular expressions. Well, that is one way, except what we have here is not regular expressions, but some function that somebody has already created that says, is this an alphanumeric character, right? So say we want to keep numeric characters as well as alphabetic characters, so we would have maybe create this function keep chars, and that's a super simple function, right? It's just a filter that takes a function and applies it to whatever input character list, and we would say input, or we would have keep chars is alpha num a1 b c prime x2 minus d, and that returns a1 b c x 2d. And that's super simple, right? And if we look at the call, so we have is palindrome all uppercase, and then we're keeping chars. And it's pretty self-explanatory what characters we're keeping. We're keeping the alphanumeric characters, and we're applying that to the input. So you might say, well, how do you find out about these is alpha num and things like that? So is alphanumeric Haskell. If you did is alphanumeric Haskell, you might say, oh, there might be something the data are package that creates this idea of we had before two upper, right? So maybe there's is alpha, and you look and there's is alphanumeric, is print, is digit, is octdigit, blah blah blah, is letter, is mark, is number, all these is. So if we go and look at is alpha, okay, it says here selects alphabetic Unicode characters, lowercase, uppercase, title case letters, plus letters of caseless scripts and modifiers. This function is equivalent to is letter. So that's great. But then is alphanum says digits that are outside of the range of ASCII as well aren't selected, aren't digits, are selected by this function, but not by is digits. So you might have more complex numbers and things like that that are handled in is alphanum there are other things that might be handled here. So is alpha num is a sort of pretty generic function that says, is whatever I'm keeping alphanumeric, right? And so we have here is alpha num because we could figure out from data char that is alpha num is something that we want to keep, right? And what do you all feel? Oh yeah, let me link to the slides. Okay, hold on. Put that in the chat here, and I'll put it also on Discord. Oh, here, let me put the Zoom link also here. Right. Let's go back to this. So we had that is alpha num or is alpha num. So we're on slide 9 right now, if you want to jump ahead in those slides that are loading. So we would keep those characters. And that's maybe a simpler way and a more clear way. And in Haskell, we always like to make things what are called self-documenting. And so what we want to do with this is make the most clear function calls and arguments that we can. And so keep chars is alpha num, pretty self-explanatory. All uppercase, sure, sounds pretty self-explanatory. Is palindrome, you have to know what a palindrome is to understand what that function call is, but we'll talk about that at a later time, about naming functions as explicitly to what they do. So maybe an alternative name. What might be an alternative name to is palindrome? Anyone know? Maybe is reverse the same or something like that. So maybe will it reverse or yeah, so who knows, but maybe something a little more self-explanatory than is palindrome.
What about bipolar numbers?
Well, yeah, bipolar numbers, right? That's that is another form of palindrome, right? And so we could name it a lot of different things. But is palindrome is okay. Numbers can be called palindromic numbers, but either way, maybe something else, naming it is palindrome might be a little too specific. All right, so now we're going to take a little side path where we're going to talk about let, where, and double exclamation mark. So you might have seen, like in Matthias's sample solutions to the homework, and some other people's examples, they might have included the word where in there. And where is interesting. We'll talk a little bit more about it in a moment, but we'll talk about let first. And let and where are not interchangeable, but offer some of the same benefits in making things more contained and easier to read. So what let does is let identifies some computation that is being defined and then used in the following section. So let is always followed by something called in, where you don't just create a variable with let, you usually create some computation. And the computation isn't executed until the in section when it gets used. And you might define several let functions, and then you might use them in the section that follows. And so you might have some main, you might have do, you might get line, C and D, and then you might have these two functions, let y equals 5 times 6. So that may seem like a variable, but really you could also do, you're having the let also do f, where x is the argument, and you take x plus y divided by y, and you'll notice that y is actually the previously defined let variable. So you can reference the other let variables or let function names within some other let variables or let function names. And then we have this keyword in, and then inside this in we can reference those y and f and c but here we're only referencing f, and then we're referencing c and d from outside of the let, and we're reading in c as a float, and we're reading in d as a float, and we're applying f to both of those and taking the sum of those values, right? So in here, if we named f something explicit about what it does, it maybe takes a float, adds, maybe we would rename f to float plus float divided by float or something like that. We could take those arguments and we apply the functions that we defined in the let to those arguments. So it's pretty clear what the print statement is doing. It's printing out what the sum of those function calls is, right? And so we've been able to define y and f clearly. We're using f clearly. And we've done that all because of the let in syntax. And so you might say, well, okay, that's great. But what if you wanted to do multiple things in the in and then refer to those values in some computation? It might not look so clear if you tried it in a let. so one thing that there's another option for, oh yeah, here, let defines y and f that will be used in the in section. And the alternative to this is where. And where says before this section, define these things. And you might have main do, you might have C and D read in, and you might have print f of C plus f of D, and then you might also have print f of D divided by f of C. And then you have this where clause that says where y is equal 5 times 6 and f of x with an input x is x plus y divided by y. And you can reuse those functions multiple times above the where. You can also include where statements or where clauses in guarded guarded like case ideas, and also case statements where you can't use the let. And so where says anywhere above this where, if these things are defined, you can use them. And so you might see guards, the pipes. Yeah, where looks more like variable assignment. Yeah, so it's true, it does. Even though let looks pretty much like variable assignment too, but it's a little more variable focused, where is more focused on the program logic, where you want to contain all the program logic all together, and then you might write your definitions or your references down below the where. So you might think of maybe the clauses in the where condition as like the references to how you do those things inside of the main body. So yeah, COBOL, some of these things are similar to other older languages, but they're pretty efficient here in Haskell. And so where says, here's what I'm doing in my program, reference this section that tells you how I computed it. Okay, so which to use, let or where? So a lot of the ethos of programming in Haskell is that you want your code to be self-documenting. We said that before. It's very important. That means if you're reading the code, you want it to explain itself. You don't want to have to add a lot of inline double dashes or blocks of comments if you don't need it. And let and where sort of help you break up your program into chunks of readable information. You could write those functions outside of the other function that you're defining, like outside of that main. You could have written y and f, right? And then just used them in the main. However, the point of keeping them somewhat close to what you're doing is that they are documenting what's going on right above it. And so it just helps people understand your code. Where has some interesting benefits. Like I said, you can use them in guarded expressions, and you can use them in case statements, and you can use them where you might not be able to use let. Okay, so we're going to now take a path dealing with lists and this double exclamation mark. Lists are really cool. We've talked about them many times. They can be constructed in simple ways, like we've seen with the consts, and we can recurse over them. But there are some shorthands that you may have seen, like the square bracket single quoted A dot dot single quoted Z gives you the result, which is a list of all A through Z characters. Z is included, so that last element, when you do dot dot, whatever the last element is, it's included in the list. So if you do 0 dot dot 10, you get 11 elements, right? Indexed from 0 up to 10, you get those values. So 10 is included. And if you leave off the right-hand side of after the dot dot, you get an infinitely large list. But remember, Haskell is lazy, so it'll never calculate that huge list. It'll never go to infinity unless you needed that infinite index or something, or some really huge index of that list. Then it would populate that list up to that index and no more, right? It would say, I'm lazy, I don't want to populate all the way to the end. But we've never seen how to index list, and usually you don't need to, since you're not writing loops, right? We're not writing loops, so we don't have to iterate over the list, so we don't have to we don't have to verify the index of something usually. But there are scenarios where it's useful. So say we had 0 dot dot in square brackets and then double exclamation mark 100, how many numbers would the initial array contain? Yeah, so it would go 0 to 100, and so at the 100th element, what would the 100th index be of 0 to 100? So let's take a look at GHCI. So we get 0, we get 100, right? And so why is that? So if we look at the 0th element, we get 0. If we look at the first element, we get 1, because 100 is the 100th element of this list. That 100 is there. So so this is what so if we did 100 exclamation mark 100, that includes that last 100th element. But say we did 0 to 99 and we got the 100th element, oh, we'd get index too large. So that 99th, even though it is the 100th element, the index 100 is 0 based. So this double exclamation mark is 0 based, right? Because the 0th element is 0. So the first element is 1, the 100th element is 100. We would get 101 elements in there, but indexed to 100. So Mario is correct. So now I want you all to play around with x dot dot y and the double exclamation mark in your GHCI for a couple of minutes, and look at different examples of what you might do. So what do you think like C dot dot F does? it'll do CDEF, but it produces the string CDEF, right? But we can still, even though it produces a string, if we get the second element, right, 0, 1, 2, that should produce what letter? E, right? And you can do, well, what happens if you do Z to A? You get the empty string because it doesn't know how to do backwards lists like that with the ... notation. There are ways, like you could just reverse the list of A to Z. You could do all sorts of things, right? So just play around with this. We'll move on, but that's pretty much what you would do with the ... notation. So the 0 to 99, the less than some element all the way up to the upper element. And so we're going to do a little more playing. So say you have a function that takes a number and a list and returns a list of the squares of the numbers preceding it up till that number. So this is thinking in the opposite of tail recursion, but it's still going to use recursion. So we might have a mapping of, or sorry, if we're just squaring numbers of the of an input list, we would take this input list and we would map over it. So like mapping is not exactly recursion, but it is. And we might do map square input list $!X. So say you have this function. Yeah, let's see, I can't remember if I no, that's not the square list that I want. Do I have this? Okay, let's make a new square list. Oops. Until. So say we have, I'm going to rename this one. Okay, so say we have square list until, and we have, it takes an int, which is the limit of where it should be stopping, and then it takes some input list, which is a square bracket int, and then produces some int, which is the element that you're looking for, the squared item that you're looking for. So you don't actually need to do this on a list. Oh yes, so without list comprehensions. So list comprehensions are something that we'll talk about a little later, Alex, and they are very cool and they are pretty self-explanatory, but we will talk about them in a little bit. So if we're squaring the list until X of some input list, we do map square input list X, and this says start mapping the squares of the input list up until this element x. So we then have where square, which is int, and square can be written in two ways. We can either have square of x equals x times x, or we could, whoops. Or we could have square x equals x to the second power, right? So we can do either one. I prefer the power 2. The problem with power 2 is sometimes Haskell requires you to encase it in a parentheses. The order gets kind of funny of operations, even though you think powers are supposed to be the strongest adherence. Sometimes it gets confused about what operates on what first. And so like function calls might get operated before powers, and even though they're not mathematical operations, it might have higher infix values, and you get all sorts of weird situations. Anyway, so we don't need it here because there's nothing after the 2 to confuse the square function. And so if we do this function, we input this square list until, and then what do we give it? So say we give it the 5th element of 10 ... 20. Okay, so this should give us the 5th element that is squared of this list, right? Or the 6th element of this list, starting from 10. And so we get 225, right? So that should be 10, 11, 12, 13, 14, 15 squared, right? And so, yep, we got that. And so that seems to make sense, right? And so this function is pretty self-explanatory, except that it might not make sense why we're doing this with a list, right? Who needs a list here to even operate on this? Or who needs a to map over something when you could just get the element? You could just do it this way, right? You could do square equals x, square x input list equals input list and then you could have whatever squared, right? That's the same, right? That's returns the same thing. You don't need the list. We're including the list because of what we're going to do next. But what's something that might need a list when you're operating on it? Anyone have any ideas? Okay, so say we have a function. What's a function that might need a list of things to get the next value of something? Yeah, you might need a map. So here's something that might need a list. So this is without folds. So we're going to talk about folds in a second. But say we have a function that takes a list of numbers and a stopping point and returns the sum of squares. I don't know if you've ever dealt with the sum of squares, but you might have sum of squared errors in machine learning. You might have that in statistics. And so you might take some list and you need the sum of squares of that list up to a certain point. So say you want the first 50 sum of squares of some set of numbers. How would you go about writing that? That's a little different than this function, right? And you can't exactly, you can use map, but say you wanted to not use map and not use fold. What might you think of doing? So if you use map, well, okay, so map is a little interesting. Map will give you at that point what is the square, right? So we could write this function as you know, just at map x squared, you know, or we could write it here. Oops, I wasn't sharing that screen. We could write this as map square 10, 20, and then we could get the fifth element, right? Oops. Right? So we could write that whole function in easily like that. So instead of writing that map where it just gives us the element, we want to write something that gives us that element plus the element before it, which was already squared. And so the list of sum of squares might look something like this. We might say sum of squares where you have an initial value or an initial list and some stopping point, right? And so we have this initial list, whatever that initial list is. That initial list could be 10 or 20, right? So that initial list could be these numbers, and then you'd want the sum of the squares. So it would be 10 squared plus 11 squared plus 12 squared, blah, 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 blah. So this doesn't really lend itself. There is a way to do it with list comprehensions, but it's not straightforward. It lends itself to either folds, which we'll talk about, or some recursion. And the recursion's a little funny because we have to recurse with an accumulator. And what this accumulator is the squared value of the item before the number you're at. And so what you need to do is, in some iteration down the line, you need to take 10 squared plus 11 squared. When you're at 11, you have to think, what was 10 squared? Okay, so you have to know what 10 squared was to add it to 11. And then when you're at 12, you need to know what 10 squared plus 11 squared was, right? And so the problem here is that you really need to keep track of things. And so we might have this secondary function defined in a where, which is sum of squares. We sometimes call these helper functions, where the iterative process doesn't include the whole function, but just includes sort of part of the function. And so we have this sum square prime, and it takes an integer and then a list and then produces a list. Now you'd think, why would it produce a list? Well, it doesn't necessarily need to, right? You could just calculate with an accumulator a plus x squared plus whatever sum of squares was of the excess. But say you wanted to write this in a little different way. So say you wanted to write this without this double exclamation mark. Say you wanted the whole list up to whatever input value top limit you had of the squares up to that point. Could you use Go? Yes, you could use Go. And you could have workers and you could do all sorts of stuff. But here, what we want to use is the power of this double exclamation mark to stop the iteration at some point. And we're stopping it at y because it's lazy, right? And it doesn't want to calculate past that. So if we go into GHCI about this function and we say, load this function sum squares, and we give it a, remember we give it an initial array, so 10, 15 to 25, right? So that's 10 elements, or 11 elements, right? And then we give it some stopping point. So let's say just to the 5th element, right? So what do we expect the result of this to be when we're calculating? So remember, we have this double exclamation mark y after the init, the sum of squares. So it's just going to give us calculation at a certain point. And what is that point? That point is at y. So this should be at the 5th element. What is the sum of squares from that beginning element up to that 5th element? And we get 1855. If we go to something like Wolfram alpha, and we say sum of squares from 15 to it should be 20, right? Or maybe it was 21, 1855. And that's what we get here when we go up to the 5th element of whatever this list was, 15 to 25. So that makes sense, right? So it's summing the squares, right? And this is the mathematical formula for that. But here we get to do like early stopping whenever we want. We could change that 20, but in Haskell, we don't change that 20. We just say, or if we were doing to 25, right? We can't get to 20 without going to, right? So we'd get like 1855 here at 20, but we can't get that value from this mathematical formula. But we can from Haskell because it allows us to stop at any point. But say you wanted to get that list of all the squares. And so you might say, well, what could we do? We could take that and remove this double exclamation mark. And so this isn't just at that point, this is the array up until that point. So if we do, I forgot to change the type. So now we're getting a list back. So now we do sum of squares. Oh, now if we did sum of squares, we're ignoring this 5, but we would get that array up to that point. But say we wanted to just get that 5th point, we might be able to do this, where we just do the double exclamation mark of that computation, which just gives us up to that point. And probably internally, it's not computing that 2296 and the 2780 after that point. So maybe this sum of squares is a little hard to imagine why we would need that list. But the next thing we're going to deal with is something that's a common computing sequence that you need. So sum of squares may not be a sequence that you need. You could handle it by just keeping track of one number, but the Fibonacci sequence is a little different. Now, this is going to be a task that we're going to try and do in groups, and we're going to understand that the Fibonacci sequence has 2 base cases. Anybody know what the 2 base cases of the Fibonacci sequence are? Yeah, 0, 0, and 1, right? The 0th element of Fibonacci at 0 elements is 0, and the first element of Fibonacci is 1. And then how do you compute the next one? So if the 0th element is 0 and the first element is 1, how do you compute the second element? So when n equals 2, does anybody remember this? Anybody know this? You do the n-2 second element and the n-1 element, and you add them together. So the next value after 0 and 1 of the Fibonacci sequence is 0 plus 1, which is 1. And then the next element, the third index, if we're indexing from 0, is the n-2, which is the first element, and then the n-1, which is the second element, is 1 plus 1, and we get a value of 2. And so how might you write this with a map and the double exclamation mark? And I'm gonna say that you can Google this. There are solutions to Google this, but I'm gonna go around and ask you what those things mean if you Google them and just write them out, and why we would do something like Fibonacci using a map and using the double exclamation mark. Okay, so I'm going to break you into groups, and we're going to take a look at this, and I'll come around to the groups and help Oops. Here's my breakout sessions. All right. Okay, everybody can join your group now. Hey, Mario.
Hello.
So this is a hard problem, right? This is not an easy.
Yeah.
That's why I'm going to go around to every group and like explain. So this Fibonacci sequence, you might use recursion, or you might use map, which does recursion, right?
Yep.
And if you Google it, you can Google it. If you Google Fibonacci
Sequence.
yeah,
I found the naive definition. Yeah.
and then and look for the one that uses map and double exclamation mark.
I found one with where.
Okay, that's one of them. Yeah, and I think it should be good.
Yeah,
Somebody's asking for help. I'll join. Hello.
Oh, hey, Eli. I think Juan might be either having technical difficulties or
Okay.
but yeah, no, I can share my screen. I already kind of got the challenge. I didn't mean to pull you away if you were with another group already.
No, it's fine. It's fine. Everybody's got to have a chance, right?
Okay. Yeah, so I mean, hang on, let me I already forgot what the challenge is.
It's the Fibonacci sequence.
Fibonacci,
We're trying to use where, the double exclamation mark, and map.
Okay. Yeah, so why is that? Okay. So yeah, Fibonacci. I think I spelled 2 C's or 1 C's. I can't remember.
2 C's.
2 C's. Yeah. Okay. And then we are just taking an integer. We want to go to how far out. Like Fibonacci goes forever, right? Correct.
It goes forever.
Yeah. So
probably we'd probably want to go to whatever element the person specifies, right?
Right. So, yeah, and I guess that's my other question is that are we returning up from the beginning all the way up to that point? Do they want a response a list or would they prefer
Okay. So yeah, let's just get a value, a single integer.
a single integer? Got it. Okay. All right. And I'll just call this n. Okay, yeah, so we would need to basically ooh, that's a now I'm thinking about it now because now it's individual. So I mean, I would like to try Go on this one only because it's a way of like retaining state and it's recursive.
Yeah. Well,
so
there will be a way of retaining state and recursive in Haskell, which just gotta wait about 10 minutes and then we'll get there.
Okay. Then let's I mean, we want map and indexing, so we want to use the indexing operator and the mapping function.
Right.
I mean, we would need base cases.
Yeah.
So, our two real base cases are if n is 0 or 1,
Right.
correct?
Yeah.
So, ooh, should I write this in a case, you think? Your case statement fair, or should I make this more?
All right. So what I would encourage.
Yeah.
There's a way of doing this where you do map.
Okay.
And then the thing we're gonna map is a helper function.
Oh, okay.
Fib.
Okay.
Call it fib. And the thing we're going to map fib over is the array.
Okay.
From 0 to infinity, because Fibonacci can go to infinity.
All the way.
And then where do we want to stop this map?
Oh. Okay.
And then in order to do this, like fib doesn't exist, right? So where would we write fib? Yeah, we could write a separate
or where, I guess,
where clause, right? We could do it. Yeah. We could do it somewhat connected. And you were talking about the base case conditions. So what does fib take? Fib takes an integer and returns an integer, right?
Yeah.
And so what is the base case?
So, so the base case, I mean, would be 0. Can you do pattern matching? You can, right?
Yeah, you can do it.
All right, yeah, so if it's 0, it's 0. If fib 1, then it's 1. And then if fib x
else, right?
Yeah. And if it's something else, then you would do yeah, because we have the n now. So we have n.
Yeah.
So oh boy. Okay, yeah, so oh my god. Okay, so we got n, which is the index we're looking at, or our pointer, and fib is the function, is the method that's going to be tossed over from map onto each one of these.
Right.
And how would you get the last if fib has been okay? So let's say like n is 3, is index 3, or yeah, let's say index 3.
Yeah. So what is n?
N is just an integer. Like it could be like 3, it could be 5. It's just an integer.
So if fib 0 is 0, is the Fibonacci of 0 0, or is the Fibonacci value at 0 0? The Fibonacci value at 1 1, and the Fibonacci at n is.
Oh, okay. So yeah, Fibonacci of that would be. I mean, does that formula work? So if I were to be like x minus 2 plus x minus 1.
So it's not the actual.
No? Not that
It's
far.
not
No.
the x, but it is the fib at x minus 2 and the fib at x minus 1.
Okay. So, okay, so fib x minus 2 plus, I'm gonna cover these in parentheses. Fib x minus 1.
Yep,
So,
and that's it.
Jesus, it's the beauty of Haskell, but that's the frustrating part, is that it can go simpler. And as I learned more like things that you could do with Haskell, like Go and stuff,
Yeah.
you get carried away and you're like, oh, let me do guards, or let me do Go, let me do something else. But this is amazing. Yeah.
So, by the way, I would take off the parentheses around fib.
Yeah.
The,
Okay.
oh no,
Oh.
the other parentheses.
This one.
Yeah, that one. That's just redundant because fib
It's
is a function.
single. Got it. Okay.
All right. So basically that's it.
Yeah. No, I
And
mean,
if you try and run it, load it up and run it. I'm going to go back to some of the other groups, but you're pretty much done.
no, thank you. I appreciate your time, Eli. Thank you. Let me see. Oh,
Hello.
Yeah, I found the 3 versions.
So do you want to share your screen and we'll talk about what they
Yes. How can I share? Can I share the screen?
you should be able to.
Yeah, I found it.
Okay.
Okay, the clear one is this.
All right.
Yeah, this.
So that's the one we're going to use part of. So you can do this, but say you wanted to be able to return the whole array of all the values. How would we modify the top one to make it,
the accumulator that you were talking about?
well, yeah, we could do an accumulator. Or we could do something where we accumulate, but we also give values. And so if we go up to the top of that file and we say, let's call this fibs, and we'll rename fibs below it in a second. And we're going to say, what do we do in order to say we want an index? So say we want the x element. So let's say fibs x. So some input, and we would do equals. Now, here's the question. So Fibonacci can return all the values up to a point. And so what we really want here, so let's rename lines 3, 4, and 5 fibs with an apostrophe afterwards. And these are what are going to be called helper functions. And we're going to put them in a where clause underneath that fibs x. All right, so now indent the lines below it. And then we're going to say, we're going to use the power of map. So we're going to say map fibs apostrophe, and then we're going to give it an array, right? Remember, Fibonacci operates over an array, right? And we can start wherever. So you can give it a number to start at. You can give it 1, sure. Sure, you can give it 1 to 50. All right.
Maybe it's so big.
So delete the space on 2, and I think you got to indent 3, 4, 5, and 6, and 7. All of them 1 more in. And the where as well. Okay. So if you did this and you ran fibs, so let's reload. And now try fibs of, well, yeah, fibs of 7, right? So the thing is, it's not going to give us up to 7, right? It's going to give us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? It's giving us all of the values. So how do we stop this at a certain point?
With the take, like
We could do take, you can do take, but I want us to use the double exclamation mark.
okay.
So where do we put the double exclamation mark?
Here,
Sure,
like 7.
sure.
What do we say?
Sure. Or X. Let's say X is your value.
Yeah.
Okay. So now let's see what happens if we reload. Right now it's giving us what that evaluation is at that 7th element. But if you look at it, if you count up 1, 1, 2, 3, 5, the 7th element will be
13.
Well, remember it's zero base.
Yeah, true.
So it's the 21, right?
Yeah.
Okay. So it's giving us the right value. But what it's doing is it's just pulling out what that value is at that element. So this is interesting because what it actually does is it stops calculating the 34 and 35. It never calculates them. And it prevents us from doing or it gives us the opportunity to do something that you couldn't really exactly do in another language without using like break statements and things like that. You can change that 1.10 to 1 ... and have that list be infinite. And then you could get fibs of 100. You could reload this and get fibs at 100. Takes a minute.
Yeah, it takes some time, yeah.
But
But big.
but it will give you, and it will not calculate that infinite list past 100. You can do Control C, but if you want, maybe do a shorter, maybe do fibs 20. Right. It'll never calculate an infinite number of Fibonacci numbers. It'll just calculate up to that point. Because it's lazy and because of the way map works, the map will say, hey, we're not going to calculate past this. All right. So that's the cool thing about Haskell in there. All right. I'm going to go join another room.
One thing I checked, and I think where in Lisp doesn't exist. I had this doubt.
So where
existed let? Yeah, of course. But where? I don't think exists in Lisp.
Oh, in Lisp.
Yeah.
Where's my scheme book? I have this book
I had
somewhere.
that doubt.
Yeah,
Or at least I was not able to find.
yeah, let exists because
Yeah,
scheme is or Lisp is very in line, right? Everything is in line.
exactly. Yeah, it's and then and
So
finishing this is bracket.
yeah, the where really is like a syntactic sugar.
Yeah, sure.
Whereas let is these are the operations that you're defining.
Mhm.
And so in Lisp, you would have let, but where couldn't exist because you couldn't offset some calculation to later.
Yeah, exactly.
You couldn't do that with Lisp.
Yeah, where is it's quite interesting where,
Yeah.
yeah, but
Yeah,
I like more let.
I think where is prettier than let. I think
Oh, really?
it looks cleaner to me.
Oh, okay. Good.
All
Thank
right,
you very much.
no problem.
Thank you.
I'm gonna check in with another
Yeah.
group.
I stop sharing.
Hello. Hello, everyone. How's it going? Going well? Oh, you posted in the chat. Okay. Let me- Oh, in the Discord chat? Ah, okay. Yeah. Okay. All right, definitely. Yeah. So you could do map Fibbo, do that. Yep. If you wanted to use a where condition, how might you redo this? You might do, let me just make it a little more compact. You might do something like what I put in the Discord chat as well, where you might have that map being done as the function call, and then the where being the helper functions that do the operation. But yes, definitely the way you did it with the Fibbo definitely works, right? And it's basically exactly the same. All right, good job. I'll bring everybody back in a right now. All right, so all of you might have come up with something like this, or you might have come up with a slightly different variation where you had some map that used some function that took an array and gave you some value, or as some value at a certain point. So we might have had this where you have the value where you take the value at a certain point, right? So because of eta simplification, we can leave off this x and just have the the map there. And we might have a where condition, or you might have defined this fib prime or fib o somewhere else. And you probably had the base conditions where the 0th element is 0 and the first element is 1, and any element after that is the fib at a prior element and the fib at 2 prior elements. And so that's basically the way that you would handle Fibonacci. And this way we're using this double exclamation mark and this 0 dot dot here to be a way to stop the map at a certain point. So map, remember, iterates over elements up to a certain point. We need the prior element and the prior element in order to calculate the next value. So we need that list, right? We need that list of elements so that we can accumulate them to get up to a certain point. And so it's hard to think about. It's hard to sort of come up on your own with this solution, but it is very very valuable to think about. And now we're going to talk about folds. So some people have said, well, wouldn't it be great to do this in Go or something where you could have state and hold on to state and just accumulate them and have a reduce function. And that's basically what fold is remember we talked about map and reduce, where map creates new values and reduce takes those new values and processes them down into some single value, summary value, informational value, something that's important about the information. And so we never did reduce before, so this fold is new, right? And reduce says you operate on the things you mapped over and give some useful piece of information about that data. In Haskell, the reduce is fold, and there are 2 methods to fold. There's fold R, which means right-hand fold, and fold L, which is the left-hand fold. And you might think, how do you do different handedness of folds? Well, we'll talk a little bit about that, but really the point is that we generally have fold R, and there's a statement that is it's the right hand fold, but it's also generally the right fold. So it's generally the fold that you want to do. And the reason is, if we take a look at the information about fold R, we would say, okay, it says it takes some class that is a foldable T, where fold R has this signature A to B in a function, and a B and some TA and a B, and you might say, okay, the foldable class represents some data structures that can be reduced to a summary value 1 element at a time. Strict left associative folds are a good fit for space efficient reduction. Okay, so wait, this statement here is getting huge and confusing. So let's take a look at maybe the end of this statement that says, lazy right associative folds, that's the fold R, are a good fit for co-recursive iteration or for short circuiting. And remember that double exclamation mark stops that map from happening. That's what we call a short circuit. We're going to say, let's stop after we process an initial subsequence of the structure's elements. So whenever we're doing some list up to a certain point where it's what we call left, the array is sort of left associative, meaning basically that you're consing on to some original element up to an empty list that you make a list from. Remember, that's how we constructed a list. That left-hand first element, it's left associative because that left-hand element will be the first element. And so the right associative folds say, if we're going from left to right, we're going to want to stop as early as possible from the left, starting at the left-hand side. Okay, so that's really complicated, really confusing, right? Really like, what's going on here? Well, let's just dive into how to use Foldar. What does that signature mean? That signature A to B to B, B, T, A, B, that's confusing. This is the most difficult signature we've seen. So here we have that signature and we have the arguments. So let's break apart what the arguments are. We have some function that has two inputs, an A and a B, and produces a B, right? That's pretty understandable. It's got parentheses in there, so we know that's what it is. And then it also takes an argument that's a B, right? And we call this argument the accumulator. And the accumulator, if you see that B, is the same type as that B that is the result of this signature. And so then we take TA, and T is considered a foldable class constructor. So generally, whenever we're folding over things, we're folding over lists. So a foldable A you can think of as a list of A's. So we have this function, we have an accumulator, we have a list of A's, maybe, and then we have the result of this fold, which is a B. And so that sounds good, sounds great. We can get a value out of a list of A's and accumulate them in a B that then gets returned at the end of the process of Foldar. So the result is a single B element, right? It is some summary of what those mapped over values are. And so how do we use Foldar? So we need to, we'll think back to that function. So remember that the sum of squares function, where I said maybe there's an easier way to do this than this function that sort of lists out the sum of squares and takes the sum of squares and reattaches it to a list and blah, 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 blah. Okay, that's pretty hard. And so what we want to do is make it easier. Okay, let me get there. Okay, so what is the function for a sum of squares? Anybody have an idea what that function would be? All right, I'll give you the function. We would take it, so we know what the signature is, right? So what type is B? So B is some result. If we're doing sum of squares, it's a number of some kind, right? It's probably, let's say it's an integer. Are A and B the same type? Remember that foldable TA means a list of A's. And so you're calculating the same, they are the same type probably when we're dealing with the sum of squares. So remember, A is a foldable type, and it means it's an array. So you might have X and Y are both integers, right? And you might have X squared. So this fold R takes the element that you're on the array and puts it in the first element. So that X is whatever element of the array that you're on, and Y is the accumulator. Remember, B is the accumulator type. And so X and Y are the two values you're operating on. And so you're taking X squared and you're adding it onto Y, which is the accumulator. And what does this return? It returns a new B. And that B, remember, is the type of accumulator. So what's the next step? So we have the first step, we have fold R and then this function. And then the next step is, what is the B that comes after the function? That is the accumulator. And what should it be at the first element? What is the initial state of the sum of squares of, let's say, no elements in a list? 0, right? What is the sum of squares of no elements? 0. And so we get to the third step. So we now have fold R and then some function, and then the zero accumulator. And this 0 is pretty common when you're doing any type of addition, or you're doing any type of not multiplication, right? Multiplication, what would your initial state probably be for your accumulator if you're doing, 1? You would have the identity, where 0 is the addition identity. So if you've taken linear algebra and things like that, and you dealt with discrete math, you know that these identities matter. So 0 is the addition identity, the groups, right? And then, so you have some foldable A, which is a list of A's as the step 3. And so what might this foldable A look like? So maybe 0 to some element, it doesn't matter, but if you wanted the sum of squares from 0 to some number, that's probably what you would do, right? 0 to some number. And so let's say 0 to 5, fold R, that's great, right? And so one thing you can do, so say we, let me get out of here, oops. Say we do this, fold R, square plus Y, 0, 0 to 5. What do we get? We get 55, which is the sum of squares from 0 to 5, right? If we wanted to short circuit this thing, it says, hey, wait, we can't do that. But what you can do is make sure that you're talking about, oops, the elements you really want to short circuit on. And the way you short circuit with fold R is a little different. And we'll talk about that at another point. So you can't do the short circuit on fold R. However, you can do something called scan R. And scan R returns the values up to a certain point. If you did scan R, fifth element, so that's up to 4, right? Then you would get the 25. So if you did scan R, 0 to 5 of the squares, hey, this is backwards, right? You're thinking, hey, how come how come this array is not the sums? Well, the truth is what fold R does is it starts with the right hand value and adds to the left. And so the scan R shows that right-handed, and scan L shows the left-handed, but the left-handed is way different, right? So the problem with scan L is what becomes the X and what becomes the Y are different. So scan L takes the X element, which is the accumulator in this version, and Y is the element of the list. And if you look at the difference between fold R and fold L, you'll see here that fold R takes the value on the left and adds it to whatever the incrementing value is on the right. And so it becomes a right triangle, whereas the fold L, if you look at the addition, oh, there's no good explanation of what fold L looks like. It'll be the opposite pyramid of addition. And so fold R is what we want, right? Fold L, we have to switch around that function, but we can do, oh, yeah. Oh, on the web page or on the
Yes, yes, in the web page.
okay. Yeah, there wasn't a good explanation though. So fold R, fold L. So
Thanks.
if we have here fold R, it adds, so the first element plus fold R of the accumulator, but you notice that the accumulator stays 0 all the way to the end, to the empty list. So it's 0 plus the empty list. And so that's why when we do scan R, we get 0 plus the empty list is 0. And then we get 1,000, which is actually the highest square, right? 5 squared, right? So 5 squared is 25, plus 0 is 25. 5 squared plus 4 squared is 41, right? So 4 squared is 16 plus 25 is 41. So you keep going left till you get the value that's in the 0th position because of this direction of addition. Whereas in the scan L, it'll be the calculation of the accumulator happens left to right as opposed to right to left. And so that's why when we do scan L, we get the 0, 0, 1, 5, blah, 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 because the 0 plus the empty list is 0, 0 plus 0 squared is 0, 0 plus 1 squared is 1, 1 plus 2 squared is 5, and it keeps going that way. So the accumulator is being added up before it adds the square of the value rather than the other direction where the accumulator happens last. Okay, so that's the difference between fold R and fold L. And yeah, Dorian put up there the definitions for fold R. So we looked at fold R, which is A and B to B and B of, right? So we had A to B and B, which is the accumulator, and some foldable A and some B. Whereas if we look at what the information is about fold L, we see that it's B takes in a B, which is the accumulator, and an A, and returns a B, right? So the B is still the accumulator. And but you'll notice that the direction of this function here is different. And the reason is internally, it's doing that addition to increment the accumulator earlier in the process than what the fold R does. Fold R waits until the very end and accumulates back towards the front of the list. And so that sum of squares that we defined earlier was much easier, right? Here in this fold R than it was in the sum of squares function that I wrote out. You can do you can do the sum of squares in other methods. So we saw the scan R, the fold R. The scan R returns the list, which is every iteration of the addition in the fold R, every element that would be evaluated. And the scan L is the every element of the fold L that would be evaluated. So you can look at what is being calculated. If you just swap out the fold R with the scan R, you can see what's occurring. That's that. Okay, so I couldn't really come up with a coffee related idea for fold R or scan R. So you might have to give me a day to come up with a coffee thing. I've been trying to think about it, but if anybody has any ideas about a coffee related fold R or accumulative evaluation, that would be great if you could suggest it on the Discord. I'll keep thinking about it for tomorrow. If I can't come up with anyone, yeah, I like my sugar with coffee and cream. Yeah, but we'll come up with something. So I couldn't come up with a homework, and I'm sorry about that. So I'll keep thinking. But next week is a little bit different, right? Next week, we're talking about what projects you'd like to do rather than coming up with like assignments and group examples. We're going to talk about sort of where we are now, like what we know. We know a lot of things now about Haskell. We know the where, we know the let, we know the fold Rs and the fold Ls, and fold R is like one of the most powerful things that Haskell has. It's one of the most important features of Haskell as being a calculative language that does things in an iterative manner that is valued. Yeah, one of the infinity stones. Yeah, it's very important. So map, foldar, very important structures, very important functions of the Haskell ecosystem, and you'll see they're used almost everywhere. And unfortunately, I don't think Plutus has this idea of foldar. And so a lot of what happens when people write Plutus scripts as opposed to Haskell scripts is the off-chain stuff will deal with the folding of, say, all of your UTXOs at something. You'll fold up all of the values of the UTXOs, and you'll get somebody's you'll get some value at a script address, or you'll do something like that. So what Plutus will do is get all the UTXOs, and what Haskell will do is say, hey, now you have a list of UTXOs. Why don't I accumulate what is the value at that script address, or something like that. And so Haskell will take the values that are provided by Plutus and do real Haskell on them, whereas you don't on the chain in a script actually do any of the foldar or anything like that. So this is where the combination of Haskell and something like Plutus script produce a really good ecosystem for building things. However, if you're having trouble with sort of running Plutus, if that's like on the back of your mind, trying to get everything running, you can take a look at my LinkedIn post on why it's so difficult to run the Plutus ecosystem, the Plutus application backend and things. Feel free to look at that. And we'll meet next week, but remember, think about before then projects that you might want to do, maybe using some of this, maybe using Plutus if you're familiar with Plutus, maybe using some other set of libraries or modules. You can definitely search around on the haskell.org or the Hoogle and search for different libraries that might do different things and see if your idea might be one of those things that you can achieve, and just keep your mind open about sort of what you want. And it doesn't have to be coffee themed, but if it's coffee themed, it's better. Although like me trying to find a homework for this one, it's pretty hard sometimes to find coffee related themes. So, okay, that's it for today. Anybody have any questions? I'm going to stop recording now.